Welcome to the class on artificial neural networks and reinforcement learning. In this video, I will introduce the SARSA algorithm, a reinforcement learning algorithm that's widely used in applications. Just remember what we said about the case of the one-step horizon problems. We start at a state S, we take a single action and arrive at a final state S prime. The best action depends on the Q values, but the Q values are not known. Therefore, we have to estimate the Q values, and the way we estimate them is by an iterative update rule, where we compare the actual reward that we get on that path with our current estimate of the reward. And if the actual reward is larger than our current estimate, then we increase our estimate, and eta is a factor that's called the learning rate, for example 0.5 or 0.01. Now this was the one-step horizon case. Now let's turn to the step of multiple time steps. In the first time step we start at S, we decide to take action A1, we arrive at S prime, but then we take another action that leads us maybe to another state S double prime, and the same kind of logic applies as before. The Q values are important. The Q values, however, are not known, and therefore we have to estimate them. And the way we do this estimation is with some iterative update rule. But what is this update rule? Let's try to develop this update rule. And I would like to start from the diagram. So this is the Q value for this branch, S action A1. And I would like to link it to the Q value in the next state. The next state is S prime. That's where we landed. We decide to take action A3. Well, Q of S A1, the Q value up here, is related to the Q value down here. What's the difference? Well, the difference is that on the way, on this link, we have got a reward. Maybe the reward was 0, but in general, we may have got a reward here, the reward at time t. So from the diagram, we can read off a Q value, Q of S A1, which is approximately the Q value in the next state, S prime, A prime. And the difference is that there's also this extra reward. And there's another difference, and that's we should discount the Q of S prime, A prime. Gamma is its discount factor, for example, 0.9. Okay, this is our approximation. And now let's shift this Q value here from the left-hand side on the right-hand side. So we would have 0 equal to RT plus gamma, and then we have Q of S prime A prime minus Q of S A1. Okay, and now let me propose an update. So what I propose is that we say I update my delta Q of S A1 if the actual reward that we get is larger than this difference. Okay? So I say let's put in brackets this RT plus gamma, and then I have Q of S prime A prime minus Q of S A1. And this is my proposed update rule. Let's just check what happens if reward RT, say, is larger than this difference. What is then? Okay, if RT, if this reward is larger than this difference, then I will increase the Q value up here. So the difference between the Q value up here and the Q value down there should be explainable by the reward that we get. If the reward is bigger, that means the Q of SA1 was not big enough. I want to update it. So in that case, we get an increase of Q of SA1, and that's the way it should be. Intuitively, that should make our estimate better. So we have the Bellman equation that links the Q value up here, which is on the left-hand side, with the Q values one step down. And this is an exact equation. It depends on the two branching ratios. One of the branching ratios is given by the policy, and the other branching ratio is given by the intrinsic stochasticity of the environment. Even if I know that I've taken action A1 starting from state S, there are still different possibilities. And then if I end up in state S prime, then I go from there. But I could have ended up in a slightly different state. So the Bellman equation links the Q values at two different levels, but just as in the single horizon case, the Q values are not given. These branching ratios that we need are not given. The reward probabilities are not given. And the solution is we use an iterative update, which is this rule here that I have motivated on the previous slides. It was not a proof, it was just a motivation. And so the idea is now we walk in the graph with this policy P. So we walk down, and whatever we do, we just continue. And each time we walk down, we update the Q values. But it's always, so once we are here, we can update the Q value up there, because we need to know the state S prime and the next action A prime before you can update the previous Q value, Q hat of SA. Q hat here on this slide, just to remind you, that's an estimation. The real Q values would be the ones of the Bellman equation. So I compare the Q value up here with the Q value down there. And I remind you that the Bellman equation is just an explanation, a mathematical formulation of this consistency condition of Q values across neighboring states. And this SARSA update rule is there to make the Q values of neighboring states more consistent. And to do that, you have to work with a small learning rate eta, a small parameter eta. Okay, and here is the SARSA algorithm, a famous algorithm of practical importance. You initialize the Q values, and then you start from some initial state. S, say this state here. You choose your action according to a policy. Say you choose this action here. Then you observe the reward, and you observe the next state. And now in the next state, S prime, you choose according to your policy the next action. Say it's action A3. And once you have chosen this action, you have all the information to update the SARSA rule, where you need the Q value at S prime A prime, you need the reward R, and you need Q. So now you can update the Q value up here to Q of S and action A. Then you rename your variables and you go back to step 2. You continue across the graph. You play more actions, more states, and each time when you are in the next state you can update the previous state. This is the SARSA algorithm. It's used in many applications. You have to play many episodes and then you stop when the Q values have converged. Now let's see what this algorithm does in a sequence of states. S1, you can take an action A1 that leads you to state S prime. From there, again, action A1 leads you to a state, say, S double prime. And from there, again, action A1 leads you to a final state, S triple prime, which happens to be the goal state. I call it the goal state because the sequence terminates here at the goal, and it's also a goal because you get a reward of 1. Now, in each of the states, in each of the intermediate states, you also have another action called action A2, and this action A2 leads you always back to the previous state. And now, suppose we start in this state S1 and we use the SARSA update rule, and we always pick the action that looks most promising right now. So we would play greedy. In practice, we wouldn't do it, but it's just for the sake of this little argument, and you break ties stochastically. In particular, since we initialize the Q values at 0 at the beginning, once you're in this state, you would compare the Q value, well, it's still 0, so you would choose equally likely the Q values. And now let's walk down. What happens? Well, I start in this S1, in this S state 1. I take action A1. That's my only choice there. I'm now in state S prime. I decide another action. Say I decide to take action A1. And now I'm here. And this is the moment where I can update my Q values. Okay, let's update the Q values. What do I see? Well, on the way there was a reward 0. So this is 0. I've initialized that 0. I've initialized that 0. So delta Q of this value up here is 0. There's no update. So I have this cool update rule, but nothing happens. And then I'm in state S prime. For the sake of the argument, let's suppose I choose again action A1. And that leads me to the final state S triple, which is the goal state. And now this time I do have an update. Okay? So now I have, going back to the SARSA rule, I would have a reward which is 1. Q was 0. Q S prime was 0. So I have an update by eta. So suppose eta was 0.5. That now means that this Q value here, that would be updated by 0.5. And so you see that the information that there's a goal at the end moves upward, but only one step at a time. I only have changed this Q value here. I have not yet changed the other Q value. And now I need to start a second episode. Walk down again. Maybe I do a loop. No, I will walk down because now I have my greedy policy. So once I'm here, I'm bound to walk down again because here I have a different Q value. And so now what happens is that in the second episode, already at the first transition, the Q values are updated. And after the second episode, Q values have been updated also 2 steps away from the goal. So with this SARSA algorithm, information flows back slowly. If you have only a reward at the end, it flows back 1 step at a time per episode. So it looks like it's flowing back slowly, but nevertheless there's a theorem which is valid for small eta, small learning rate. Suppose the SARSA algorithm has been applied for a very long time, using updates of the normal SARSA update rule. Now, if the learning rate eta is small, and if we have played long enough so that the Q values have converged in expectation, so on the expected update is 0 for all states and action pairs, then the set of Q values solves the Bellman equation with the current policy pi. And this is a cool result. It means you can play this online algorithm SARSA, which is very easy to implement. And if you do it long enough, and if you decrease the learning rate eta after some time so that it really becomes small, then in the end, you know it will converge to the Bellman equation. And by the way, where does the name SARSA come from? SARSA is just a sequence: state, action, reward, state, action. SARSA. Let's finish with a quiz on the SARSA algorithm. Here again the update rule. Now suppose we have initialized SARSA and played for many steps, at least 3 steps. Is the following true for the next steps? And we do the first 3 together, the first 3 questions. In SARSA, updates are applied after each move. In SARSA, the agent updates the Q values Q of SA related to the current state. In SARSA, the agent updates the Q values Q of ST-1, AT-1 related to the previous state once it has chosen AT. Now think for a moment and then we do it. And here's the answer. Yes, in SARSA, updates are applied after each move. You play as you move along. At every move, you apply the update. But it does not apply the current, you don't update the current state, you always update the previous state because you need to know what's the next state and what's the next action. 2 further questions. In SARSA, the agent moves in the environment using the policy pi of SA, and the answer is yes. And SARSA is an online algorithm. Again, this is true. It's not a batch algorithm. You don't have to wait until the end of the episode before you can do something. As you move along, you update online. So it's online, and it's because you use the policy, it's also called on-policy algorithm. So what have we seen in this lecture series? Reinforcement learning is learning by rewards. The world is full of rewards, but labels are sparse. So most learning in the real world is based on rewards. Reinforcement learning works with agents that take actions, and the agent learns by interacting with the environment. The notions are that you have discrete states S, discrete actions A, and you have rewards at every transition. Many of these rewards might be 0. When you do online exploration, online estimation of what's good, then you have this trade-off between exploration and exploitation. In principle, the best action is the one with the highest Q values, but you don't know the Q values because you don't know the reward probabilities, and that's why we need to explore. Now the Bellman equation gives the self-consistency condition for Q values, and the SARSA algorithm evolves towards these self-consistent solutions. And you do this while exploring the environment with the current policy, completely online, iterative, a beautiful algorithm.